All right, so we'll get started. It's my pleasure to introduce Matthias Eimi from Stanford. He'll be presenting Are We There Yet? Towards Foundational ML Models through Accessible, Community-Involved Big Databases. And Matthias is a professor in the Department of Mechanical Engineering at Stanford and the Department of Photon Sciences at SLAC National Accelerator Laboratory. He comes to us with degrees in mechanical engineering, computational engineering, and a doctorate in mechanical engineering. And his research interests are broadly on the computational modeling of reacting flows, the development of numerical methods, and the investigation of advanced energy conversion concepts and molecular processes. He has received the NSF Career Award, the ONR Young Investigator Award, the AFOSR Young Investigator Award, and the NASA Early Career Faculty Award, the Hiroshi Tsuchi Early Career Research Award, and the Bessel Award of Alexander von Humboldt Foundation. And so, Matthias, it's our pleasure to welcome you to the LEAP lecture. The stage is all yours.
Thank you so much for the kind introduction. Let me share my screen. And I hope everybody can hear me okay.
Yes, we're good.
Perfect. All right. Thank you for inviting me to present at this meeting. Really appreciate this. What I'd like to do is give you an update on some research focus that we have been working on over the last couple of years. And this really is concerned with how can we provide databases in order to support machine learning tasks of different kinds. So with this, it was already mentioned, just by way of background, our research and work is largely concerned with fluid flows, turbulent reacting flows, energy conversion systems. And just to motivate this entire presentation, I just want to give you a couple of typical examples that we are thinking in our research group. So this starts out with sustainable energy utilization. For those of you not familiar, let me just take my cursor here. For those of you not familiar with this, this is a gas turbine where we're thinking about converting this from hydrocarbon fuels to hydrogen. What we're seeing here in the middle is a renewable fuel sources. So these are batteries where you're seeing molecules interacting with catalytic surfaces. But if you're looking to other applications, such as emissions of pollutants, smoke, or advanced propulsion concepts, that are all applications that we are interested in. Furthermore, we're also looking to decarbonization processes, especially in the context of industrial heating, where we have a huge CO2 source by CO2 emissions, but also applications, especially here in California, the aspect of wildfires and environmental flows is of big concerns. So what you're really seeing is there are different facets of reacting flows, environmental flows. And what we like to do is to see whether machine learning or data-driven methods can actually help us to move the needle to make some progress in different aspects. Okay, so with this, what you're mostly seeing here on this in this talk is ideas on how we can support machine learning tasks around this aspect of fluid flows more broadly. And the main question is, how do we get the data? All right. So with this, let me just make a little sidestep here on the different knowledge discovery paradigms. And this is really around this idea on how can I learn or describe some of these complex fluid flow processes that I motivated in the previous slide. So we can distinguish between available knowledge, and in our language, this essentially means fundamental physical principles. So if we have a lot of this physical knowledge, then it's only natural to use physics-based approaches. And I think many of you are certainly familiar with the idea of Navier-Stokes, chemical reacting flows, chemical mechanisms, which typically have a foundation in fundamental principles or first principles. Right? So this is one axis, and we have been exercising this for centuries on using physical principles in order to derive physical laws. The other axis represents available data, and this really is the idea that in the absence of physical knowledge, we can essentially resort to data. And again, in the limit of knowledge sparse informations, relying on data is quite useful. Typically, what we like to do is combine both aspects, data and knowledge, and then we are moving in this idea of knowledge-guided or data-driven approaches, where we leverage available physical knowledge and data, but come up with better principles that are perhaps more adaptable, deal with more current processes, or explore different areas. Okay, a couple of examples again from our field. I call this energy science and engineering. You can think more broadly on thermodynamics or thermochemistry. We have been using data for decades by now, and this started out with thermochemical tables, where this has been data for different physical properties, thermodynamic properties, has been acquired in painstaking experiments using some of these thermodynamic processes, phase transition processes. But if you look closely, also chemical mechanisms. These are data that are typically extracted from rather extensive experiments. Moving in more recent areas, what I'm showing you here is a snapshot of an data accumulation task where we essentially looked to available DNS data. And for those not familiar with DNS, this essentially refers to direct numerical simulations. Think more broadly about high resolution simulations of reacting flows here in this context, where we're essentially seeing that over about the last 20 years, we as a community were able to acquire a large set of a large corpus of simulation data, which essentially exceeds several terabytes of data. Right? So this is quite interesting. And the question then is, well, how can we utilize this data in order to advance our knowledge in the field of chemical reacting flows? Okay. For this, one natural choice is to explore machine learning methods or data-driven methods. Just to provide a brief overview, typically I like to characterize this in 3 categories: supervised learning, this entire area of classification regression. We have unsupervised learning, clustering, dimensional reductions, which is very popular in our field, especially if you're thinking about large thermochemical manifolds, complex chemical mechanisms, but also complex thermochemical state space relations. This clustering and reduction is quite helpful. And there are different methods for applications. And the last task is perhaps most exciting. This has to do with semi-supervised learning, where we're using essentially partial informations and trying to self-regress knowledge or extract knowledge. One application is reinforcement learning, super resolution models, or generative approaches. And I will talk about some of these approaches as we go along in this presentation. Okay. So then what is the challenge? And I kind of like to characterize this in 3 major challenges. The first one is, if we are using purely machine learning approaches for those applications, we typically encounter 3 challenges. The first one is regression errors. And this really means is that our models that we are constructing, perhaps from a limited set of data, is limited in the flexibility or generalizability, and then we are typically encountering some errors. The second challenge is black box informations that the machine learning models that we're generating from sparse data is typically not too interpretive, meaning that we're encountering issues in extracting physical meaning. And the last challenge, which is really at the heart of these presentations, are the data challenges. Where do we get the data? Can we ensure that the data is of the quality that we need in order to use them for our AI or machine learning tasks? Okay, I want to give you 2 examples, or actually 3 examples on any one of these aspects. The first one is really regression errors. What I'm showing you here is a simulation of a so-called lid-driven cavity. This is nothing else than a square box, and we're moving essentially the top with a prescribed velocity. Figure on the left is an physics-informed simulation. So this is essentially a Navier-Stokes simulation. The figure on the right shows you essentially the same results, but here represented by an convolutional residual neural network. And this is essentially machine learning predictions. And what you're going to see here is this is essentially the velocity, right? So everything is non-dimensionalized, just to keep this rather simple. And you perhaps have seen some of these results before. Lid-driven cavity is just a standard simulation task, and it has very well-behaved physical information. So you're seeing a vortical structure. If you were to characterize this or represent this within a machine learning model, what you're essentially seeing is that we're encountering regression errors. This has to do with a lack of detailed information about the physics. And with this, within a very short time, you're seeing essentially that the solution diverges, and with this becomes meaningless for physical analysis. So this is one challenge, and the question is, how can we address this using larger databases, or actually moving towards this concept or idea of foundational models? The second example that I want to show you again is from an application of ImageNet, where we're essentially seeing that over the last about 15 years, we're seeing massive improvements in classifying images. And I think many of you certainly know this better than I, where we're finding that the errors essentially reduced to within better than in human performance. And this was kind of breakthroughs by thinking about deep neural networks, right? So what you could argue is an error in classifying of less than 3% is actually remarkable, and in fact it is. But if you're thinking to take the same concept and applying this to some of our energy concepts or safety critical measures, you perhaps are stuck with the question is, are 3% really sufficient in order to make predictions on rockets, propulsion systems, or as I said, some other space mission critical applications? And this is really the question that we have been thinking about. What does it take in order to incorporate another layer of safety so that we can really ensure that our systems that we are designing with data-driven techniques are actually robust in this application? Okay. Last aspect that we're finding is the availability of data. What you're seeing here is on the right-hand side, just a snapshot of available data that we as a combustion or energy conversion community have been accumulated. And I like to think about is in availability of data versus complexity. And what I mean with complexity could be geometric complexity, physical complexity, or other chemical complexities. What we're typically finding is it is fairly easy for us as a community to generate a lot of data of very simple experimental configurations. And this is really just driven by the available resources that we have in academic institutions or labs, the diagnostics, which is sufficiently simple. But as soon as you're moving to more complex systems, so you're seeing here combustors, complex geometries, and even gas turbines, it becomes increasingly more challenging to acquire high quality data. And there you're seeing essentially that at some point we're encountering this data sparsity, right? And that's really what I like to address here in this presentation, right? So with this, focus of this presentation is really the data challenge. How can we take advantage of existing data, bring this into our community, and by this have kind of a direct effect on improving our model predictions and ensuring that there are some physical principles that we can actually extract from this available data, right? So collecting more data, organizing in community, and performing benchmarks is really the focus of this talk. And with this, let me just motivate this one step further. I'm going back to the ImageNet database that I'm sure many of you have been using or have been are aware of. This essentially gives you an idea about the size of data that we typically require in order to make useful or find useful applications for data-driven techniques. And you're really finding is that we're really looking to a corpus of data, which is about 15 million distinguished images. The direct implication of this is that if you have diverse data, of course, you can advance our ability to predict this information much better. This is essentially the progression of different machine learning tasks. And this really had a huge impact on how we are thinking about data-driven techniques, how we can develop different architectures that essentially allow us to improve the predictive accuracy, but also identifying some open challenges within this large data sets. So what I want to probably drive home here is diverse data, large data is critical not only for classifications, but also for the scientific computing. Okay. Now, where are we, especially if we're looking to flow physics data? Again, this is my community that you're seeing here on the right-hand side. So you're looking to a snapshot of simulation results from the Johns Hopkins Turbulence Database. Perhaps this is the hallmark of simulation databases. This is a set of high quality, or I would almost say ultra high quality DNS data of a number of canonical configurations. So in our language, this essentially means idealized homogeneous turbulence, stratified turbulence, perhaps wall-bounded turbulence channels, pipe flows, and so on. But the physics is simple, is quite simple, right? So now if you're comparing the complexity, what we're finding on ImageNet, again, classical image classification, we're typically thinking about two-dimensional data, and as I mentioned, about 15 million samples. So about the database is a terabyte, which you're essentially fitting on a USB stick now these days. And the diversity is about 1,000 distinguished objects, right? Contrasting this with the Johns Hopkins database, we're typically thinking about four-dimensional data, this of three spatial dimensions and time. The current data set is about 500 terabytes of complexity, and it has in total 9 configurations, right? So with this, you're seeing that our data is substantially larger, more complex, but at the same time, the diversity is smaller by about 3 orders of magnitude if you're comparing this to the richness that we see in some other data sets. Okay, so then the question that we have is, well, how can I elevate this and take some ideas from ImageNet or other image classification databases and essentially incorporate this in our combustion community, right? So that challenges here are clearly the three-dimensionality, the high resolutions, and in many cases, the richness of the flow structures that we would like to preserve as much as we can. Okay. So with this, we are really proposing a new approach, and we refer to this as an BLASTNet database. This is an attempt of essentially bringing the community together to a web-based data platform for big data analysis in order to support scientific machine learning. And the idea is conceptually quite simple. The execution is a little bit more complex. So what we are essentially doing is we are essentially resorting or relying on our community, which has DNS data available. They are typically localized on servers, on DNS platforms, which is hard to access. But what we're really doing is we're essentially taking individual users for different flow applications. So this could be chemical flows, fluid flows, environmental flows. We are essentially working with this community to compress the data if necessary and leveraging existing open source databases, which provides accessible storage for our community that is typically free of charge. Here, in this case, we are using the Kaggle database, where we're essentially using this as a data platform to store data. And the key idea of BLASTNet is essentially provide an interface so that different users can access this data that is provided through this Kaggle database in a well-structured form, in a unifying form, so that it can be exposed to different machine learning tasks. So this is the idea here. We're going from a community which provides different DNS data, high fidelity flow field simulations that will be essentially created in a common data set that is accessible to the broader user community. Right? Where are we with BLASTNet right now? So this is currently an NSF effort. What we have accumulated so far is about 35 different configurations, and this is steadily growing. In total, about 14 terabytes of data, and this includes up to 6 and 29 channels. What we mean here with channels are essentially distinguished flow field quantities, velocity, pressure, chemical species, temperature, energy, and so on. Right? This is essentially a machine learning enabled data format. It's shared on Kaggle, and currently we have seen about more than 640 terabytes of downloads. So you're clearly seeing that there is quite a bit of interest from the community. What I really want to emphasize here is that this is not our database. It is really a community database, and our goal is just to curate this data in different forms. So far, we have about 15 different contributors, and this is, again, steadily growing as we are bringing on board more and more users. Right? So to show this here, this is the interface. It has an interface with the different configurations of flow problems. It has tutorials via notebooks so that users, perhaps not familiar with the data sets, can be acquired, acquainted with the data sets and the data infrastructure. and it has also machine learning models that can be used as an training set for transfer learning or to get different applications started. Right? To show you the diversity, I mentioned this very early on. It's very easy to develop machine learning models for one particular applications or for one particular operating environment. The key challenge is diversity and transferability. And I want to illustrate this here. Again, what you're looking at is in flow field. This is an homogeneous isotopic turbulence of an axial velocity in some units of meters per second. If you're looking to the distribution, typically you're finding that in this turbulent flows, the fluid dynamics or the velocity field is typically Gaussian or almost Gaussian distributed. And what we like to do is to make sure that if we're developing machine learning models, that we can access a broad range of operating conditions. So this would be Reynolds number, Schmidt number, Prandtl number, generic quantifying parameters. To emphasize the diversity, what I'm showing you here is different statistical quantities, variance, velocity, skewness. So this is the third moment, and the kurtosis is the fourth moment. These are all higher order moments that describe this fluid flow conditions. And what you're seeing quite nicely is that there is a quite large range of state space coverage, essentially meaning is that this data set that we have is sufficiently diverse so that we have a hope towards moving to foundational machine learning models so that our models that we're deriving from these data sets are sufficiently generalizable and robust, right? If you were not to do this, what you're typically using is in one of these machine learning applications is one single operating condition. So any one of these color codes or single color codes would be essentially used for exposing this to your machine learning model. Right. So importance here is that diversity is important, so that it essentially provides an avenue towards generalizations and foundation models. Right. However, what you're also seeing as well, there are still some gaps here, and we're currently working on filling this. And this could be essentially commissioning specific DNS data that allows us to fill these gaps, or designing particular set configurations that really are targeting specific operating conditions. Right. So with this, let me move on and talk about some of the capabilities. And this really evolves around advancing the frontier of machine learning tasks. And the second challenge that I want to discuss is bringing the community together so that we're working on a common data platform. Right. So benchmark and scaling. First topic is super resolution. This was from this category of semi-supervised machine learning models. And for those of you not familiar with super resolution models, what you're really taking is coarse informations, and from this we're trying to resolve fine scale structures. In our language, if you're applying this principle, instead of recovering figures on pictures or portraits, what we like to do is from our flow field simulations is that we reconstructing fine scale structures. This is perhaps best illustrated here on this figure on the right-hand side. So what we're typically having is in our fluid flow simulations is the so-called coarse grid simulations, meaning that we are not resolving all of the scales. And this is essentially just a basis on the reason that we are using filtered flow field simulations, right? So what we like to do is to use a machine learning methods in order to recover the fine scale structures. And in the simplest form, this is essentially an extension of the super resolution approach to turbulent flows. You can solve this problem with different techniques. One of them is a deconvolution technique. Here, in this case, we want to essentially evaluate machine learning approaches in order to go from a filtered solution, like think about a coarse grain simulations, to a high resolution task. If we can do this with machine learning techniques, we would have an enormous benefit, because then we have essentially a way of describing subgrid scale models or turbulent closure models, which our community has been working on for centuries by now. All right, so let's see how this works. And the idea is that we created a data set, and we call this Momentum 128. What it really means, it's a coarse sampled DNS set. It looks like this. We have essentially here our flow field for the three different velocity quantities, U1, U2, U3. So it's a three-dimensional flow field. We also have the density. Again, since we're looking to reacting flows, the density will change by combustion. And then we essentially coarse sample this with different resolutions. So we're using an 8 times filtering, 16 times coarser and 32 coarser. And what you're seeing is, if you just compare the flow fields, the pixels become larger since we're filtering or averaging over a larger domain. Okay. So this DNS data set has about 27 configurations, and it's quite manageable for different applications, right? Again, one message here is that if you're using large data sets, we have a sufficiently diverse database that essentially provides us hope that the models that we're developing can really serve as in general closure models. And this is emphasized here on this case. So we're looking to the standard deviations of the kinetic energy. So E superscript K in my language, this is the kinetic energy. And here we're looking to the mean quantities, right? So each one of the symbols is one particular DNS configurations. And since we have 27 of different kinds, we can span a wide range of flow field conditions. Okay. Interesting to do is to explore different machine learning architectures. So what I'm showing you here is essentially a number of different architectures. So in total, we essentially used existing super resolution architectures from the community and really exposing this to this turbulent flow field applications. And what I'm showing you here is essentially the ground truth. This is the kinetic energy that I discussed on the previous slide. The input is essentially the resolution, 8 times 16 and 32 times coarsened. If you're using different machine learning architectures, well, of course, tricubical interpolation is not quite a machine learning architectures. You're essentially finding that we are able to recover some of the structures that you're seeing here, right? So this is a baseline case. Here we have a residual dense block. We are introducing physical principles. An EDSR, this is an enhanced deep residual network, and different architectures are utilized. What you're seeing is, by and large, each one of these architectures is capturing the high resolution flow field to good accuracy. You're seeing some deviations if you're going to coarser and coarser input data for the reason that there's more physics to discover or invert from this cases, right? What's perhaps more interesting is to put this on a more quantitative level. And with this, since we have this very extensive data set, we can ask questions on convergence, both convergence in terms of the architecture size. So that means essentially the degrees of freedoms that we have, or the model parameters. But we can also ask questions in terms of the complexity of the data set. And this is essentially illustrated here on this graph. So we're looking to the scale similarity measure, which essentially shows that for different network architectures, we are approaching an asymptotic convergence. And this is really useful towards guiding machine learning principles on how we can use certain architectures to approximate more complex fluid flow applications. Right. So what you're clearly seeing is that certain architectures, for instance here, this Fourier neural operator has initial challenges to get accurate simulations, but only for very large data sets is this model more beneficial. If you're looking to the figure on the right-hand side, this is essentially a parametric study where we increase the size of our machine learning architecture or of our neural network. And you're clearly finding that certain architectures have a steeper slope, but all of them following on this exponential curve. And this is quite encouraging. Important thing to note here is that this essentially allows us to really look to asymptotic limits. And for this, we're relying on this large data set that is provided to this BLASTNet architecture. Okay, with this, next thing that I want to target or address is community building. What we have been finding, again, in our combustion or fluid flow community is that there's a lot of interest, but typically this barrier to entry can be quite high for several reasons. Either the data is not available, the architectures are not available, or it takes a lot of knowledge in order to calibrate or train different models. For instance, hyperparameter searching, learning rates, this is all a little bit intuitive. And we found that providing some guidance can help us as a community to make substantially more progress, right? So let me talk about our attempts on bringing community together, again, mostly around this idea of fluid flow and chemical reacting flow applications, right? For this, about 2 years ago, we started a workshop, and this workshop essentially evolves around this BLASTnet database. So this was the first inceptions, and we're calling this Flame AI. And this is a future learning approach for modeling and engineering. Really, goal is to offer this as a virtual workshop to bring a community together to exchange ideas, calibrate, and learn from different modeling approaches, and really advance our field in turbulent reacting flows for applications to energy and propulsion. Again, same topic here is super resolution. This was our first machine learning challenge. This essentially resulted in an Kaggle-sponsored machine learning challenge or an hackathon. It was actually a little bit more than just a hackathon. It was a 2 weeks event where we essentially got together and with 50 participants, and this essentially resulted in about 670 machine learning models, entries or submissions. More recently, just this year, we finished the second installment of Flame AI. This evolved around a dynamic process with application to wildfire predictions, where you're clearly seeing that the number of participants grew from our initial 50 applicants to about 500, with now 2,500 submissions. 2 messages: there's clearly interest from the community to participate. And the second message is really that those environmental flows are increasingly more interesting, especially if you're thinking about modeling, applying this to dynamical processes, for instance, fire spread rates, pollutant transport, and related applications. What I want to do is I want to just give you just a glimpse on what our community can do in order to advance the frontier. Moving back to this first Flame AI installation, where essentially those 50 participants thought about different approaches on tackling a super resolution problem. And you're essentially seeing some really interesting machine learning architectures and approaches which really advanced the field and made substantial progress beyond what we were able to do as an individual institution. This is, again, a snapshot of a super resolution task. There are different names associated. Really, associators are relate this to different participants. And you're clearly seeing is that different architectures, different ideas resulted in different outcomes. And this is quite interesting. What I want to show you here is highlight one of the key results is that different ideas essentially gelled in such an interesting architecture that we essentially found that we're getting some really interesting developments that resulted in substantial improvements in the model performance. And this came about by taking ideas from different fields, bringing this in our community, and by this advancing our ability to predict some of these complex reacting flows. And I really think this is perhaps one of the most interesting contributions that we are seeing from this applications, where different ideas essentially result in novel approaches that cross-fertilize different applications. So with this, I want to move on and talk about the last aspect on where are we currently with this BLASTnet database effort. As I mentioned, currently we're calling this essentially BLASTnet 2.0 version. Currently, we have about 35 configurations. The data size grew from 5 terabytes to about 14 terabytes. We have substantial databases and different contributions. What we're currently working on is extending this BLASTnet database not only to fluid flow applications, but also to environmental flow applications and experimental data, where we're seeing that especially experiments are fairly rich and can provide another spatial dimensions to this entire data set. Important to note is that, again, we are currently working here on extending this database by bringing in more users, more data, and building this into a full-based data structure so that it's more broadly accessible. Our long-term vision is to decentralize this BLASTnet database so that instead of having us curate the data set, that this can be done automatically. And we're currently making good progress in this area, right? So with this, brief conclusions, I believe that BLASTnet is one example on how our community can benefit from distributed data sources that have been generated over recent years, how it can contribute from open data storage systems in the form of Kaggle, and more importantly, from small efforts to help our community equip this with machine learning models, machine learning architectures, so that we can make progress together towards embracing this new paradigm. Future work, more data, more machine learning tasks, and more scientific domains. And again, I mentioned this already in the past. So last slide that I want to share here is how can you participate? Most importantly, we are always interested in getting more data, into introducing the diversity. So if there's interest in contributing, please reach out to us. We certainly want to access more data from for scientific machine learning tasks. We are currently working on installing another Flame AI workshop, typically in in the summer-fall season of 2025. And if you're interested in learning more about this, please feel free to reach out and contact us at blastnet.ml. Finally, let me close by acknowledging sponsors, DOE, the Stanford Institute for Human-Centered Artificial Intelligence, CACL, and of course NASA. NSF were major contributors in supporting this work. With this, let me finish here and see whether there are any questions. Thank you.
Matthias, thank you so much for your talk. Are there?
Thank you, Matthias. Can you hear me?
Yeah, I
Okay.
can.
So I think it's a very nice work, and I have a tiny question is, so what's the difference or how much improvement that you use the machine learning to get a more higher resolution output than the traditional interpret method? Yeah.
Oh, that's a good question. So what is the benefit of machine learning methods? Perhaps shown here in one of the slides. Let me just. So what we are really finding is the problems that we are looking at right now. Oh, sorry. Yeah, the problems that we are looking at right now is like the super resolution. And what we are typically finding is that if we have more data, we can get quite a substantial improvement. And the reason is that our physical models that we're developing are typically developed for simple idealized flow fields. Now that we're expanding our flow field environments or our parameter space, we can gain quite a bit of improvements. And if I recall correctly, so we're typically looking to Reynolds stresses. This tau SGS is in Reynolds stress. It's in subgrid scale. A term that we're looking at is what we found is there can be about an order of magnitude improvements in predicting those quantities across the board compared to our standard physics-based approaches. Right. So there more data, more diversity actually helps us to improve our model performance.
Thank you for the great talk. I have a question. So I saw that in the competition, one parameter has very low MSE, but it really has a lot of parameter, like the size of the model. So number of the parameters is huge. So I'm curious how you rate that, because you basically increase the size of the model and it's almost natural that the performance is gonna be good. And it's different by the magnitude. Thanks.
Yeah. So I think you're probably referring to this figure here.
I think it's the ones like a few slides below this, like where you have the MSE and yeah, this figure. Yeah.
Oh, this figure here?
Yes.
Good question. So this is a result from the machine learning contributors. So this is this hackathon or this machine learning challenge. What we are finding is that different users use different architectures. And I would argue that some of this model are perhaps not as well calibrated for these applications. So this is what we're finding is pure hyperparameter optimization is one effect. The second effect in terms of improving the performance is that really exploring different approaches. So this would be a mixture of experts or sample averaging, which really helped us to get some improvements on this, right? But what you're really finding is a lack of proper training is typically resulting in this poor convergence. Larger networks, poorly trained, are still providing an poor performance output.
Thanks.
Yeah.
Hi, Matthias. Thank you very much. Very interesting presentation. So, my question is, data are and diversity are very important, right? But also evaluation metrics are, and in my postdoc here at Columbia, I'm working on evaluation metrics for air system models, but not only limited to those models, right? And my question is, in your benchmark, apart comparing different machine learning models, right, on different data sets. So how do you systematically evaluate the outcomes of machine learning models? So are you using a consolidated set of metrics for doing that? Or, yeah, because I saw the SSIM as one metric, but you have like consistent set of metrics to do that? Thank you.
Yeah, a really good question. So what we are typically doing is, and I really have to talk about different aspects. So for our research, we're using different metrics to compare different models, and these are typically just overall feature similarity metrics, mean square error, but this doesn't really help us for our combustion applications. So if you're thinking about chemical flows, you need to have physical conservation, mass conservation, species conservations, elemental conservations, and this is a higher level of constraints that we are imposing. So we are somewhat more careful for our research environments. For this machine learning task that I'm showing you on the slide deck, this Flame AI workshop, what we're typically doing is we're starting out with very simple metrics, mean square error, overall characterizations, and this really helps the user who is perhaps not familiar with this idea is just to lower the barrier, right? And once we have this, we have an internal characterizations to take a more fine-grained characterizations. Scale similarity is one metric. For our fire spread models, we actually look to flame height and physical quantities so that we're getting also some physical insight. And then we also measured long-term rollout to make sure that our solutions are not converging, right? So
Thank you very much.
answer here really is that we're typically using very simple metrics so that we are bringing everybody on the same page. But in order to really make this scientifically more relevant, we are really looking to physical conservation principles.
Thank you very much. Makes sense.
Matthias, it's a very nice effort. Thanks for sharing it. I had two questions. One was, initially you sort of drew contrast against the ImageNet dataset.
Yep.
You said that for our physical applications, we have just much smaller diversity. I think it was like 3 orders of magnitude. But at the same time, the data size is like 2 orders of magnitude larger, or maybe, even more than that. And if we ever hope to get to the same level of diversity, that is there an ImageNet or maybe even like half of that? How does one surmount that like technical barrier of storing so much data, allowing users to use it? If, does your community have any plans for that?
Yeah, really good question. So clearly, you're right. So it's 2, perhaps 3 orders of magnitude, depending on how optimistic you are. We won't be able to get 1,000 different objects on high fidelity 3-dimensional DNS data. I just don't think it's feasible. But what we are typically doing is right now is that by leveraging community storage databases, we essentially just reducing the footprint of some of the available data resources. And I think this BlastNet is kind of one attempt where we are clearly not there at 1,000, but we are at 50 right now, 50 different cases. So we're making some progress. We are a little bit more selective on what we're storing. So we're typically storing only a few snapshots. But if you're asking about predicting time dynamics results, where you have to tip time sequences, that's a huge challenge. On this note, what I really think is BlastNet is a demonstration on how we can use open source distributed architectures in order to make a foray, and we close the gap by an order of magnitude, right? In order to reach this final approach on equivalence of ImageNets, what I believe is we need government sponsorships. We need broader centralized compute architectures, storage architectures, and I believe that DOE has some attempts on bringing this data set creating some of this large server architectures for facilitating this.
Thank you. And the other question I had is also, I guess, related to this. So
Mhm.
you framed that there is this like regression error that's there. And maybe, in our heads, there is some hope that if we get to larger and larger data sets, these regression errors will get smaller. And now that you can look at these asymptotic scaling laws, is it possible to make a prediction that, how large of a data set do we need to get a regression errors? I know that that's not what you showed, but if you think about regression errors and at some point ML is performing just as good as like a numerical model, how far are we from that?
That's a really good question. I mean, this is I haven't thought about what is the asymptotic data size. One reason that I'm struggling with this is that fluid flows are a little bit weird because we don't really have this taxonomy. That means those flows come in different facets. And if you're asking for general, I want to predict any fluid flow to a certain accuracy, that's a tall order to answer because you could think about flows that are involve complex geometries, complex flow physics, complex initial and boundary conditions. And if you're really trying to make this as general as possible, you're setting you up for failure. What I would perhaps do is look in the category of flow problems that we are curating here with this BLASTNet thing, which are all typically from one category. It's typically like a quasi one-dimensional flow, has very little geometric complexity. And then I could think about that we can ask the question, well, how much data do I need in order to populate this entire state space, for instance, this one here, right? For this case, I think we're pretty close, especially for HIT. We're showing that by combining physics and data-driven methods, that you're within a reach. And from our scale similarity analysis here, especially for some of the super resolution cases, asymptotically, we're kind of seeing where we're moving towards, right? I think a diversity of 100 different data sets for HIT cases, it's a great starting point, and we're getting within a few percent of accuracy.
Thank you, Matthias, for a wonderful presentation and all our guests for a great conversation. Matthias, we have your contact information, so if people have questions, may they reach out to you?
Absolutely, yeah. If you have any questions, and if you want to share some data, we'd love to talk to you.
Wonderful. Thank you so much. Thanks, everybody.
Thank you.